Okay, PS3 is due today and tomorrow. Any questions or problems? Yep.
Can I just ask one clarification on problem set 4?
Okay. Problem set 3?
Sorry, 3-4, I'm sorry. When it's asking what's the cost of all the merging per layer, is that for every single merge or just for one specific subset, I guess?
Well, when it's asked for all the merge of a particular layer of the recursion tree, it's asking for all the merges at that level of the tree.
So the whole layer, okay, I'm just making sure it's not talking about just like half of it ringing towards it.
Right, what you're doing is analyzing the recursion tree one layer at a time. Any other questions? All right, so one thing I'll point out is there are two things on this problem set where you're finding a big O-bound on divide and conquer algorithms, but without using the master theorem. And one of them is the one where you're doing the selection on two sorted arrays, and the other is the one he just mentioned where you're doing a merge of multiple arrays. So why is it that I'm not just having you use the master theorem for these?
Doesn't always work. Doesn't always work.
Well, why? Okay, so it doesn't always work, but why doesn't it work in this case? In these cases? Yeah?
It doesn't perfectly fit the master theorem, so you go ahead and work out some other way of that.
Yeah, but what is it about this that doesn't fit? Yeah.
It's because you have the K and
Yeah, they're two variables, right? So you've got the two variables, and it's not gonna, the master theorem doesn't exactly work. So you have to fall back on sort of more manual techniques to do it, which is what I'm sort of guiding you through. Any other questions? All right, yeah.
Are there style points associated with Chaos problems?
No, he asked if there's style points. No, your grade's based entirely on the test cases, but realize that the last test case is worth half the points. So if you do all with the last test case, let's say you graded out of 20 most of the time, then you get 10 points. So there's a big premium on getting it to pass all the tests. All right, we're going to start a new topic today that goes along with chapter 3 in the book, and it's graph algorithms. Okay, so here is a graph. So what is a graph? You've seen graphs before, you've studied graphs before. So what's a graph? Yeah?
It's just like a group of connected nodes.
Okay, a group of connected nodes. Okay. What's another take? Yeah?
A graph is a set of nodes and a set of edges.
Okay, set of nodes, a set of edges. Okay. Any other takes? Yeah?
Just a display of how things are connected to each other.
Okay, a display of how things are connected to each other. Yeah?
Well, an abstract list of pairs that can be connected using the edges.
Okay, so a list of pairs that can be connected via the edges. You might just say it's a list of pairs, where the pairs are the edges. I mean, these are all fine answers. I'm just trying to get at you that you have some intuition about what a graph is. So here's a formal definition. It's a set of vertices and a set of edges, where an edge is a pair of vertices. And, you know, some people say node, some people say vertex. I tend to say node for trees and vertex or vertices for graphs, but it's not that big a deal. So in this one, you see there are 7 vertices, which I've numbered 1 through 7, and then there are some number of edges that connect them. And the way graphs are used is to represent relationships among objects. Now, when we study graphs, we'll be using V for 2 purposes. V is either going to stand for the set of all vertices, In this case, it'd be the set containing 1, 2, 3, 4, 5, 6, 7, or sometimes it'll stand for the size of that set, the number of vertices. The book actually will put vertical bar V, vertical bar for the size of the set, but it's always clear from context whether I'm talking about the set or its size, so I won't bother. And similarly, E stands for the set of all edges or the number of edges. So in this case, there's V and there's E. There's E. Okay? So that's all formal definition. The size of V is 7, the size of E is 9. So because there's a set of vertices and a set of edges, each with its own size, when we look at algorithms for graphs, we'll see that we have to express the complexity in terms of both E and V. So often there'll be two variables in the complexity measures that we have. However, they're not, we'll see shortly, they're not completely independent. I mean, obviously, if you don't have any vertices, you're not going to have any edges. And so the number of vertices puts a limit on the number of edges there can be. And I guess I'd say we'd see that shortly. Here we're seeing it. E is O of V squared. So let's be exact about it. If you have, say, 2 vertices, how many edges can you have? Yeah.
How are you doing your graphs? Are they directional? Can you have multiple?
Okay, so it comes down to whether they're directed or undirected. So we'll hold that question. We'll look at some examples of graphs and we'll come back to that. But in a lot of our complexity derivations, we'll take advantage of that fact that E is O of V squared. And that'll let us do some simplification sometimes. We can just, if we're looking for an upper bound, we can sometimes just replace E with V squared. Okay, let's think about uses for graphs. So there are various kinds of graphs and various kinds of uses. So what I'm doing here is there are 7 states in Australia, and each state is represented with a vertex, and the edges, well, what are the edges? Why is there an edge from 1 to 2 and not an edge from 1 to 7? Yeah?
Because one doesn't touch 7 on the map.
Okay, so 1 doesn't touch 7 on the map. So 1 and 2, basically 1 is Western Australia, 2 is Northern Territory. They have a border, so we have an edge between 1 and 2. But Western Australia and Victoria don't have a border, so there's no edge there. All right, so this kind of graph is called an undirected graph. There's no directionality. If Western Australia borders Northern Territory, then the opposite is also true. So no arrowheads on the edges. The edges go both ways. Yeah, that's one kind of graph, undirected. Here's a directed graph. This is an old visualization of the web. It may be as old as 20 years, but the idea is the vertices are, I'm not sure exactly what he did for this visualization, but let's say that each web page is a vertex. And there's an edge from one web page to another, from one vertex to another, if it's possible to click on a link on this page and go to that page. So if you can click on a link on page A and go to page B, then there'll be an edge from one to the other. So if you pick 2 random web pages on the web, how likely do you think it is that via a series of clicks you could get from one page to the other? I heard a not great. Anyone have any other idea?
Fairly likely?
Okay, so we go from not great to fairly likely. I think it's closer to fairly likely. And studies have been done of this. And indeed, if a page has any link at all out into the greater web, and Google indexes that page, via Google at least, you can get basically anywhere from just about anywhere. So it's a pretty well-connected thing. Anyway, I don't know how the colors or whatever were chosen, but it's a direct. The point I'm trying to make though is that this is a directed graph. Because you can go from page A to page B doesn't mean you can go directly back. It's a one-directional thing, and so that's why the arrows have arrowheads on them, one direction. Okay, here's another one. This is a directed graph, but it's also acyclic. It's a special case of a directed graph. So I just argued the web has cycles in it. But a prerequisite graph, such as this one here, does not have cycles. So here the vertices are courses, and the arrow is prerequisite of. So 1 is a prerequisite of 2. And 2 is a prerequisite of both course 3 and course 4. And so on. But it's not cyclic. There's no way, once you leave 1, there's no way to get back. Once you leave any vertex following an edge out, there's no way to get back. No cycles. Now, why would it be kind of bad to have a prerequisite graph with a cycle?
There'd be a course you could take.
Yeah, there'd be a course, like if course A depends on course B and course B depends on course A, you couldn't take either one. Because you have to take, the rule would be you have to take one before the other, and that rule would apply to both. So anyway, acyclic graphs are a very important subset of the set of directed graphs. Right? Here's a graph that shows the distance between major cities in Texas. So here our vertices are cities, and our edges are major roads. So I guess 1 is probably Amarillo maybe, and 2 is Lubbock. I'm not exactly sure which ones I used, but well, I guess that's not it. Looks like I didn't use real data. Oh, I see what that is. Fort Worth, yeah. 1 is Fort Worth. So, and this is not just an undirected graph. So why would you expect this graph to be undirected? Generally, if there's an interstate from one city to the other, there's one going back the other way. I don't know of any one-way interstates. Certainly one-way city streets. It's weighted, though, because there's information on the edge. In this case, it's distance. So sometimes we associate information with each edge. And then we ask questions like, what's the shortest path? So a graph like this, although, well, if you think about Google Maps and similar things, when it's trying to find the fastest way to get places, it's using a map like this. It's probably a directed graph because it's got to take account of one-way streets and cities. It's definitely a weighted graph. Okay, I just postulated the existence of one-way trails. I think I've seen one-way hiking trails in the past. Certainly one-way biking trails. So here we have an edge from 1 to 2, and it's weighted, so it's directed and weighted by time. So it takes 45 minutes to hike from 1 to 2, and it takes 65 minutes to hike back from 2 to 1. Okay, why would that be? How could it take a different amount of time to hike back? Yeah, it's uphill. And then we have sort of a cycle of one-way trails connecting 2, 3, and 4. So an example of a directed weighted graph. Okay, now let me get this to work. We've seen lots of examples of graphs. Let's stop now and consider what is the difference in the way they are used from a graph and, say, a binary tree in a computer program. And clearly they're related. Formally speaking, a tree is a kind of graph. But binary trees tend to be used for very different purposes than do graphs. Yeah.
Trees are more for storing data, where graphs are more for representing relationships between data.
Okay, he said binary trees are used for storing data versus graphs representing relationships between data. Okay, let's get some other takes. I mean, this is kind of just it's not a formal question. Yeah.
Normally when you're conversing a tree, you're either going like all the way down or all the way up, versus in a graph you can pretty much go anywhere as long as you're finding a path across rather than.
Okay, so you're picking up the the special structure of a tree. Yeah?
The tree has a root where a graph you can kind of start anywhere.
Okay, a tree has a root, by nature of being a tree, a graph doesn't. Yeah?
Trees are sorted.
Trees can, you can have trees so they're sorted in a way, yeah. Yeah?
With the tree, there's only one way to get to a certain destination, but with the graph, there's like 10.
Okay, trees, there's one way to get to a destination, graphs multiple ways. Where in your program would you use a tree? A binary tree? Why would you use a binary search tree, say? Yeah?
Quickly find some single element.
Quickly find some single element. In other words, you tend to use trees in programs to make them faster. Right? You're not interested in representing a tree from outside the program, typically. You're interested in, it's just a data structure that you can use to make the program run faster. On the other hand, graphs are typically used in programs not to, they're used to represent information from outside of the program, information about the world, the information you're talking about. So it's just, they're put to different uses. And if you look at libraries for programming languages, you will find, tree set and tree map, implementations of binary search trees. You typically do not find graphs. You don't typically find a graph class in the library for, say, in Java or C# or whatever. And that's because graphs, the particular graph to use for a situation is going to be different every time. And it just hasn't, I guess the designers haven't found it advantageous to have a class called graph. All right, now there are two ways to, actually before we do this, let's go back to the question I had at the beginning. If you have two vertices, let's say we're using a directed graph, how many edges? What's the most edges you can have? Two vertices A and B. Well, you could say 2 or 4. Clearly you could have an edge from A to B and an edge back from B to A. But you can also have self-edges. So you could have an edge from B to itself and from A to itself. So in a graph, the usual assumption is you don't have multiple edges going the same direction between two vertices. But you can have self-edges. So the most you can have is n squared. So essentially, every vertex can have an edge to every other vertex. And if there are v vertices, that would be v squared edges. That's where the maximum number of edges comes from. All right, there are ways, you have to represent graphs inside of programs. And so one way to do it, a common way to do it, is with an adjacency matrix, basically a two-dimensional array, a two-dimensional list. And so in this case, we're just, we think, I'm just using one-based indexing here, so think of the first row as index 1. So row 1 contains what information? What's that? Okay, so row 1 contains the edges out of 1. So there's no edge that goes from 1 to 1. There is an edge from 1 to 2, and its weight is 45. And then there's no edges from 1 to 2 or to 1 to 3. And similarly, row 2 has the 2 edges that leave vertex 2. So it represents the connectivity, and if you pay attention to the numbers, it represents the weights on the edges. So that's one common way to represent a adjacency matrix. The problem with this representation is it consumes v squared space. Obviously, it's a v by v array. And that's okay if there are lots of edges. But a lot of times, most times in fact, there are not a lot of edges compared to the number of vertices. And you end up with just lots of empty spots like you see here. Sometimes it's appropriate, but more often, what am I doing here? Okay, forgot what I was doing. Okay, that's one example of an adjacency matrix. Here's another one where we're not storing the weights anymore. So this is what an unweighted directed adjacency matrix looks like. So there's either an edge or there isn't. So this would just be an array of booleans. Okay? Okay, this is undirected and weighted. So you can think of an undirected edge is really just shorthand for two directed edges. So you can say there's an undirected edge between 1 and 2. What this means is there's a directed edge from 1 to 2 of weight 50 and one back from 2 to 1 also of weight 50. And you end up with that look right there. What property does the adjacency matrix for a undirected graph have? What symmetry does it have? Yeah?
So symmetric across the diagonal?
Yeah, it's symmetrical with respect to this diagonal. If you folded this corner up to that corner, everything would match up. And that's an undirected, unweighted graph, just zeros and ones, but still symmetrical. So all these consume v-squared space. The other more common way to do it is with an adjacency list. And so now you have a list which is v long. There's an entry in that list for each vertex. And then for each vertex you have a list. I drew it as a linked list. It doesn't have to be a linked list. Some kind of list of the edges that leave that vertex. So you can see that vertex 1 has an edge to 2 of weight 45. Vertex 2 has 2 edges, one to vertex 1, one to vertex 4, and so on. That consumes theta of E plus V space. So what's the, where does the theta of E plus V come from? Yeah?
So along the top you have one block for each vertex.
Okay, so the top is your theta of V.
And then each of those list elements is an edge.
Right, there's a list element for each edge. And so it takes the space for the edge is proportional to E, the space for the vertices in that list is proportional to V, so E plus V. So that's an adjacency list. Here's one without the weights. There's an undirected one with the weights. The symmetry isn't obvious here. It really isn't the symmetry, but you'll notice here I have 5 edges, there I have, what did I have here? I have 5, 1, 2, 3, 4, 5. I would think okay, some of these are one way. Anyway, here I have more edges. Because if there's an edge from 1 to 2, there's also implicitly an edge from 2 to 1 that I have to store. And there we are without the weights, the undirected graph without the weights. So there are all these variations on the theme. All right, so let's think about which is better. Which of these representations is better depends on the nature of the graph you're trying to represent. So here's a couple of terms for you. We're going to call a graph sparse if it has O of V edges. And we're going to call it dense if it has omega of V squared edges. So what am I really saying here? What makes a graph sparse? Yep.
If the graph is sparse, that means, or like, I should say, if the graph is dense, that means every vertex has an edge to every other vertex.
Well, okay, so what he said was if a graph is dense, that means every vertex has an edge to every other vertex. Not necessarily. I mean, a graph that contains 1/4 or 1/8 V squared edges would be considered dense. So the deal is it's dense if, yeah?
Oh, I was just going to say if every vertex is represented with its other vertex, so whether it has an edge with it or not, like zeros.
Yeah, you don't have to have, there's a difference between being dense and having, having a vertex for every vertex, having an edge between every pair of vertices. So it's dense if, this always refers to as the graph grows. So as the graph grows, the number of edges is proportional to the square of the number of vertices. So if you're representing something and as it grows, you keep representing it, if the number of edges stays proportional to the square of the number of vertices, so 1/4 V squared or V squared or 1/8 V squared, whatever have you, then it's dense. On the other hand, if it's proportional or better, if it's proportional to the number of vertices, then it's sparse. So if there's 5 V edges or 10 V edges or 1/2 V edge. That's sparse. Also, if it stays constant, we call it sparse. Okay, so if you have a dense graph, how much space will it take to store the dense graph in a matrix? V squared. The answer is always V squared for a matrix. How much space will it take to store it in a adjacency list if you have a dense graph?
V squared.
Okay, where does the V squared come from? Yeah.
It's the upper bound on the number of vertices for each edge.
Okay.
Compared to the number of edges.
So we know if it's dense, if it's in an adjacency list, it takes O of E plus V space. But if the graph is dense, we know that the number of edges is proportional to V squared. So for a dense graph, this just becomes O of V squared plus V, which simplifies to O of V squared. So if you have a dense graph, even your adjacency matrix is going to take V squared space. So which should you use? What's better to use? Let's say you're representing just connectivity, no weights. Is it better to use a matrix, which takes theta of V squared space, or an adjacency list, which takes theta of V squared space? Yeah?
Depends on if time is a factor in your case, because the adjacency matrix would be accessible in constant time.
Okay, the nice thing about adjacency matrix is if you're interested in finding out is there an edge between some pair of vertices, it's just a single lookup in constant time. That's the advantage of the adjacency matrix. For a list, you're going to have to search one of these lists to find the thing you're looking for. Yeah?
Well, the matrix will also take up less space for a dense graph because the list structure needs a bunch of pointers essentially, which
Okay.
is 4 bytes. Boolean is probably only going to get represented as 1.
Right. There's a space advantage for a matrix. The matrix is just, in this case, would be a 2-dimensional array of bits. If you're, or bytes, depending on your language. Whereas with the adjacency list, you've got pointers flying around. So yeah, the space is proportional to V squared, but the constant's bigger for the adjacency matrix. So if you know your data is going to be dense, you might as well use a matrix. On the other hand, if it's sparse, if you're dealing with a sparse graph, what does this simplify to? We know something about E if the graph is sparse. What do we know about it? Yep. Yeah, it's O of V, so this becomes O of V plus V, which is O of V. So if it's sparse, then we got that for a adjacency list, but it's still V squared. Really, it's really theta of V squared for a matrix. Yeah.
Is it possible to perform matrix operations on, if it's stored as a linked list as opposed to a matrix?
Well, so sometimes there are algorithms where you want to do things like multiply the adjacency matrices together. And those operations are much more natural in a matrix and clumsier on a list. So that would be a consideration too, depending on if you're trying to do that operation. All right, so which is more common in nature? Things to represent with sparse matrices or things to represent with dense matrices? Yeah?
Sparse matrices.
Okay, sparse. Let's think about it. What about a graph where the vertices are cities and the edges are airline routes between those cities, direct, non-stop flights between those cities? And make this a graph of the world. Is that a sparse graph or a dense graph? Okay, I'm not saying there's an edge if there's a way to get from one city to another. There's an edge if there's a non-stop flight from one city to another. It's sparse, right? There are far more cities in the world you cannot fly to from Salt Lake, without landing first, than there are that you can fly to nonstop. And if you go to a smaller city, St. George, let's say. I don't know where you can fly from you can probably fly to Salt Lake and maybe Phoenix, I don't know. But certainly not many. So that graph is sparse. What about the vertices or web pages and the edges are, there's a reference on one page to the other. Sparse or dense? Incredibly sparse. I don't know how many trillions and trillions of web pages, but no web page has trillions and trillions of links. What about the vertices are electrical outlets, and there's an edge between a pair of electrical outlets if there's a single wire, an uninterrupted wire going from one to the other. And you're talking about the University of Utah, all the buildings at the U. Very sparse. Okay, can someone think of an example of a dense one? Yeah?
It's maybe like a list of how similar things are to each other. So like, test how similar like everyone in the room was to somebody else.
Okay, so if the vertices are the people in this room and the edge is, there's an edge between two people if they're similar to each other. Depends how we define similarity. If they're similar, if similarity means that they're both human, then that would be a dense graph. Okay? Or you could go back to the airline example. If you've got cities of the world and there's an edge between two cities, if you can fly some way between those two cities, perhaps by making multiple stops, and you restrict yourselves to cities with airports, that's a very dense graph as well. You can pretty much fly anywhere with an airport. But bottom line is that most in common experience, most graphs are sparse. All right, now we'll do our fair share of analyzing graph algorithms. So let's warm up by analyzing some simple ones. So here's some simple operations. Is there an edge from vertex U to vertex V? I say that on a matrix, that's omega of 1. Or not omega, theta of 1. And it's just because you can index to anything in that matrix in constant time. So that's a theta of 1 thing. What about on a list? What's the argument for a list? How long will it take to find out if there's an edge from one vertex to another in an adjacency list? So I said it's better, it's O of V, doesn't take longer than V, it doesn't take longer than E, it takes at least constant time. Well, it certainly takes at least constant time. How do you argue that it's O of V in the worst case? What's the worst case?
That vertex is connected to every other vertex.
Okay, which causes what? What property of the adjacency list? Which edge is the worst one to look up? So what do you say?
All of them are in a single list for one.
Okay. So if you got a long list, if you're trying to find if there's an edge between vertex U and vertex V, you're going to have to search through this list. So you go to vertex U and then look down this list to see if you can find V. And if it's at the very end, it takes a long time. How long can that list be? Can there be more than V things in it? No, because that's you can't have more than V edges out of a vertex. Could it be longer than E? No, because each one represents an edge. You can't have more than that. So that's where those two upper bounds come in. And it just depends on the relationship. You could have lots of vertices and very few edges, in which case that O of V bound would be tighter, or vice versa, in which case O of V would be tighter. What about, is there an edge out of U? So we don't even want to, just want to, is there some edge out of U? What's the cost in a matrix? Yeah?
Well, this is the reverse, right? If you're in a matrix, you have to search down the entire row or column versus if you're in a list, you just go check the element and see if there's a listing.
Right. So in a matrix, you're basically searching a row to see if there is a 1 anywhere in it. Is there an edge? And if it's full of zeros, you'll have to search the entire row fruitlessly. That's going to take V time. And for a list, though, you just go to where you want to go and see if there's a null there. Or is the list empty? Okay, what kind of list you're using. That takes constant time. So some operations are faster than others. What about enumerating all the edges out of a given vertex? Say printing out all the edges out of a vertex. Why is it take V time for a matrix? They go across the whole row. And for a list, you've got to traverse an entire list hanging under some vertex, and the same arguments that went with the first one apply. It just depends on how long the list is. What about finding all the edges? In other words, consuming the entire data structure, visiting every corner of the data structure. Well, clearly, for the matrix, it's V squared, because they're V squared elements, and for the list, it's V plus E, because that's how much stuff there is in the list. All right, now we're going to look at a higher level algorithm. This is called explore. So explore works on in this case, we're going to look at undirected graphs. And the job is to, given a vertex, systematically visit every vertex that's reachable. And there's my algorithm, and we're going to assume that I have an array called visited. It's a Boolean valued array that tells us that initially everything is false. So basically it's going to tell us when it becomes true, that means we have visited that vertex. So let's see how this works. So we're exploring out of A. We're trying to find everything you can reach from A, which is going to be A, B, D, C, and E in some order is going to be visited. So first thing we're going to do is mark V is initially A, so we're going to mark it as true. So, hold on. Okay, rather than have a visited array, I'm just use yellow to mean it's been visited. So A's been visited. Don't worry about what PreVisit means right now. I'll talk about that in a second. Then for every vertex out, if we haven't visited it, we're going to recursively call explore. So what's going to happen next? I already showed you. There are two vertices out of A, edges out of A. We can either go to B or D, and I'm just going to say when there's an arbitrary choice, we'll do it in alphabetical order. So we're going to call explore on B. And what's the first thing that will do? It marks B as visited. Now it's going to try to explore everything out of it. So it'll first try to go to C. It hasn't been visited, so it recursively call explore on C, mark it as visited. It's going to try its edges, but it's not going to find anything that's unvisited connected to C, so it'll return from the recursion, and B will try its second direction. It'll try going to E. And that works. Now the recursive call for E is going to try to go to B. That doesn't work. It's going to try to go to D. That works. Now we've recursively called explore on D. It's going to try to go anywhere, and it can't. There's nowhere unvisited left to visit, so it'll return, and eventually it'll return all the way up to the top. So what we've identified, we have systematically visited every vertex. And the edges that we actually used, I'm going to call tree edges. They're the ones we actually traversed. And the white edges, I'm going to call back edges. We didn't use them. So notice that explore just systematically visits every vertex in some clump. It doesn't, it didn't get to F and G over there because there's no way to get there from A. So that's our explore algorithm. Now, what if we want to systematically visit every vertex? Not just every vertex that's connected to some given vertex, such as A. How could you use explore so that it visits everything? Yeah.
Just do the same thing, but start at each node. So start from A.
Okay.
Explore, start from B.
Okay, so the idea was we could, given a graph that we need to visit every vertex in some systematic fashion, we could just take the first vertex, say A, and explore out of it. Then you would look at B. Now, would you try to explore out of B? How would you know that it would be fruitless to explore out of B?
It's already visited.
So it's marked visited already. So you're looking at that visited array. So after you explore the first vertex, now you're looking for some other vertexes unvisited, and you would find F. And so you then call explore of F. So by repeatedly calling explore on unvisited vertices, you'll end up visiting everything. That's DepthFirst Search. So DepthFirst Search is this explore method with this with DFS up top. So you see what DFS does is it just marks every vertex unvisited, marks it false, and then it iterates through the vertices, and if it finds an unvisited vertex, it explores it, just like we just said. So it's going to DFS calls explore of A, and then we get a bunch of recursive calls that explore everything there. Then what's going to happen? After all those recursions terminate and we're back up in this loop.
It's to either G or F.
All right, it'll keep searching along the list. In this case, we'll say it finds F first. So then it will call explore of F, which will find the G, and then we're done. So that's DepthFirst Search. It visits every vertex in the graph. And it's not enough to say DepthFirst Search is something that visits every vertex in the graph. It visits this in a certain way, and it uses, so the order in which operations happen is important. These pre-visits and post-visits are important. We're going to use them for a given purpose, for an important purpose we'll see shortly. Okay, but that's the basic DepthFirst Search algorithm. Okay? Are there any questions I can answer about it? We'll be sticking with this for a while. All right, let's do something now with our DepthFirst Search. Turns out we don't do DepthFirst Search typically just because we want to visit every vertex. We're doing it to extract information about the graph. In this case, what I want to do is I want to color. I want to find the clumps that make up the graph and color them different colors. So I want to have like a yellow clump and a pink clump or something. Those are called connected components. So I'm just changing the algorithm slightly. You can see right here, I say I have this variable called CC that starts out at 1. So that's the connected component number. CC is 1. And every time I find an unvisited vertex and explore from it, after I finish exploring it, I increment CC. And then the only other thing it changes is I've defined PreVisit. So what PreVisit does is it stores the current value of CC into this array CCNum. So it's going to associate a connected component number with each vertex. And the idea is we want A, B, D, C, and E to have the same connected component number, and we want F and G to have a different connected component number. So if we do our DepthFirst Search, and let's say the connected component number 1 is represented with yellow. So it makes this call to explore, and then down here, every time we visit a vertex, we're storing yellow. We're coloring the vertex yellow. So because I'm actually showing you there. We're storing the number 1 as a connected component number. And then we're sort of out of searching here. We come back up to this loop. We add 1 to CC to make it 2, and then we explore out of F. And then we'll be storing 2s right there. So there's an algorithm to identify the connected components of an undirected graph. You just take DepthFirst Search, add a little bit to it, define PreVisit, and you've got that algorithm. So that's our first graph algorithm. And that's very similar to, we're going to make lots of use of DepthFirst Search that way, by instrumenting it to do what we need to do. In this case, I want to know the clumps. Here's another thing I'm going to do. Pre-visit and post-visit times. So we're going to have 2 events associated with each vertex. There is the time at which we first visit the vertex, when we first encounter it, which is when explore is called on. So when you call explore of G and vertex A, at that time, that's when we have first encountered A. And then you search out of A, and when this call to explore that where V was A gives up and returns because there's nothing else to do, that's when we're done with A. So we're going to associate a pre-number will be the time at which we first encountered A, and the post number is the time at which we were through with A. Okay, and the way we do it is we have a variable clock which starts at 1. Every time something happens, well, when we first encounter, we call PreVisit. When we're all done, we call PostVisit. And when you call either one, all you're doing is storing, and for PreVisit, you're storing V, you're storing the current clock time into the pre-array at index V and the incrementing clock, and a similar thing for PostVisit. So that'll associate two numbers with each vertex, the time at which it was first encountered, the time at which it was last encountered. So let's watch how this unfolds. What vertex do we visit first? A. So we call explore on A, and it gets a pre-visit time of 1. Okay, now it's going to explore its neighbors, and when there's an arbitrary choice, we'll make it in alphabetical order. So it'll visit B next, and what's its pre-time? 2. Then it's going to go to C, and its pre-time is 3. Now what happens? Right, we will try to explore out of C. There's nowhere new to go, and so we're done with it. But when we return, we do post-visit of V. So what's going to change about C? Right, it'll get a post-visit time of 4. Now we're back at B. What happens? Okay, we're not done with B yet. We go to E, and it gets 5. We go to D, it gets the 6. Now we're done with D, so it gets the 7. We're done with E, it gets the 8. We're done with B, it gets the 9. We're done with A, it gets the 10. So those are the pre and post visit numbers. Then DepthFirst Search searches for an unvisited vertex and finds it at F. What pre-time does it get? So it gets the 11. G gets the 12. The post time of 13. Post time of 14. So those are pre and post numbers. And we'll see shortly what use you can put these to. All right? So you'll be doing lots of pre and post times. So any questions I can answer about how they work? Okay, I'm going to, let's take a break right now. I'm going to do this analysis next week. We'll do something else after the break. Okay, so what I skipped over was the analysis of the complexity of DepthFirst Search. And we will come back to this. I want to go ahead talking about DepthFirst Search on directed graphs because the catalyst problem for next week is a DepthFirst Search on a directed graph. I want to make sure that I talk about that so you can get started on that if you wish. I know from past experience that people will go to that catalyst problem and ignore everything I had to say today. Okay? I'll be explaining the right way to do algorithms on specifically DAGs. And if you try to sort of invent your own way of doing it, it's not likely you'll invent a way that's good enough, that's fast enough. So this is crucial for the catalyst problem, at least. Okay, so we just looked at what it looks like to do DepthFirst search on a undirected graph. Let's try it here on a directed graph. So, same ground rules. We're going to do our DepthFirst search. We're going to, when we got an arbitrary choice to make of what vertex to visit next, we're going to go in alphabetical order. Okay? So we'll visit A first, and its pre-number will be 1. What will happen next? We'll go to B. It'll get a pre of 2. I'll explain probably next week about these colors as well. There are things I'm going to have to skip over to get to their big payoff. Okay, so we go to 2. Now what? We got to explore out of B, and C is the next in alphabetical order, so it gets a pre of 3. I'm coloring the edge black if we actually end up using it instead of backing up and giving up. What happens now? There's nowhere to go from C, so it gets that post time of 4. Then we'll explore, we're sort of back at B now. Now where? Yeah, we go to E. It gets 5. From E, we go to D. Well, I'm sorry, we try to go to C, and that doesn't pan out, so I'll color that orange. Now we try to go to D. That works. It gets a 6. We try to explore out of D. That doesn't work. I'm coloring it orange. We're done with D. It gets a post time of 7. Now, back at E, what happens? We're done with it, so it gets the 8. And then back to B, nowhere to go. Back to, so it gets a post time of 9. Back to A, tries to go to D. That doesn't work out. It gets a 10. Now what happens? Okay, now we're looking for an unvisited vertex, and the only one is the next one we find is F. So it gets the 11. We explore to G. It gets a 12. It tries to go to E. That doesn't work. We get a 13. We get a 14, and we're done. All right. Now, the black edges are the ones that we ultimately were useful. The orange edges are dead ends. So if you ignore the orange edges, what can you say about the black edges? Just look at the edges right here, the edges in this clump. What can you say about the black edges? What do they form? It's an acyclic graph. A tree. Okay? It's a tree rooted at A. Similarly, this is a tree rooted at F. So it's sort of, what this is called is this is a DepthFirst search forest, multiple trees. So it's a forest. The black edges are sort of the DepthFirst search tree, a bunch of DepthFirst search trees. I'm going to come back. There are ways we can classify things, which I don't want to get into today because there's more important things I need to get to. Okay, let's see what we can do. I want to talk about DAGs today, so we're going to skip detecting cycles because there are no cycles. Okay. So we know that a directed graph with no cycles is called a DAG, directed acyclic graph. And we saw that they represent relations that involve priority, such as that. We want to, the fundamental algorithm on DAGs is called topological sort. And topological sort is putting the vertices into a list such that no vertex has an edge to a vertex that comes earlier in the list. So if you had to put these into an order that had that property, so all the edges go from the vertex to things later in the list, what would come first? What would come first in a topological in a DAG? Okay, A could come first for this DAG. What else could come first? Yeah?
Any vertex that doesn't have an incoming edge.
Any vertex that doesn't have incoming edge. So you could put C first or F first. They don't have any edges out, so they could. No, it won't work. Yeah, it has to be, I'm sorry, it has to be anything that doesn't have an edge in, not an edge out. So yeah, you got to do A first. Okay? And in fact, there are three possibilities that I have here. They all start with A. You can go A, D, B, E. So all of them start with A, D, B, E. Why is that? Why not A, B, something, something? Because, yeah, you have to go to D before you can go to D. So A has to come first. The only choice, B and D both have edges from A, but B also has an edge from D. So you have to go to D next, and then B and then E. Then you have some choice. Once you get to E, you could go to C next, or you could go to G next. So the three possibilities just sort of permute G, C, and F in some way. Clearly, F has to come after G, but E and C can come in either order. Right, so any of those three are called topological sorts. And yeah?
So when it's choosing the next vertex to go to, is it based off of the number of edges in? To that tool, like, does it go to the next vertex with the least number of edges in?
Well, we'll see an algorithm for doing topological sort. I haven't shown you that yet. Right now I'm just defining topological sort. And the property we have is that if something appears in the list, all the edges from A must go to things later in the list. All the edges to B that come out of B must go to vertices later in the list. That's the property. That's the definition of topological sort. Topological sort is important because when we do DAG algorithms, we want to do them in a particular order. Sometimes it's good to do them from the beginning of a sort to the end, and sometimes backwards. But they almost always involve a sort. So here's a couple of definitions. A source is a vertex with no edges coming in. So this graph only has one source, that's A. A sink is a vertex with no edges going out. C and F are the sinks here. What if you had a graph with one vertex and no edges? What would be the sinks, the sources and sinks? Yeah, that one vertex would be both. It'd be a source and a sink. No edges in, no edges out. All right, let's look for a topological sort algorithm. Bottom line is, this doesn't make sense because I didn't talk about the, no, I can. In a DAG, it turns out every edge leads to a vertex with a lower post time. Okay, and we're going to use that to our advantage. I'm not going to worry about the proof. So let's try it out. It doesn't matter what arbitrary choices you make when you do the topological sort. So I'm going to do reverse alphabetical order and see what happens. So we'll do the search starting at 1, starting at G. It gets the pre-time of 1. Now what? We'll go to F, 2, 3, 4. Okay? If we're going in reverse alphabetical order, which one we do next? E, So E gets the 5, now what happens? C gets the 6, it's done, it gets the 7, back to E, it gets the 8. Okay, now let's do D. E gets a 9, B gets the 10, and 11, a 12. And all that's left is A gets 13, 14. So in a linearization, in a topological sort, well, in a DAG, every edge leads to a vertex with a lower post time. Okay, let's see if that works out. We go from 14 to 11, we go from 14 to 12, we go from 11 to 8, from 8 to 7, and so on. And it doesn't matter what arbitrary choices you make. Every edge is going from a higher post time to a lower post time. So how could you take advantage of that fact to topologically sort a DAG? Yeah?
Just go in descending post-time order.
Right. Do a DepthFirst search. Keep track of the post times. You can ignore them. You have the pre-times too, but ignore them. And then just put them in descending order. And so descending order, the A will come first, and the what's the lowest? The F. The F will come last. Okay. So topological sort. Typically, a DAG algorithm involves doing a topological sort, and then doing something to each vertex in that order or in reverse order. Now let's do it by making arbitrary choices in alphabetical order. So this here, A, D, B, E, C, G, F, is if I just order by these post times. Let's do it the other way now. So now we visit A first, then we go to B, then from B, where are we going to go? E. From E, we're going to choose C arbitrarily, so it gets a 4. We're done with that, it gets a 5. We back up to E and then go to G. That'll get the 6. F will get the 7. We're done with F. We're done with G. We're done with E. We go back to B. We're done with it. We go back to A. Then what happens? We go to D. It gets the 12. We're done. It gets the 13. And A gets the 14. And the numbers are different. But what topological sort do you get? Let's see, we get A, go in descending order, A, D, B, E, G, F, C. So we know there's 3 topological sorts possible for this graph. We've derived 2 of them. It just depends on the arbitrary choices. And it doesn't matter which you get, you're just doing them, getting the post times, and doing the ordering. Now, is a sorting algorithm needed? Suppose you're doing a topological sort. What would be the easy way to get the vertices into topological order? Yeah?
Maybe just as you traverse, well, like within your node plot, just keep some kind of int variable and then just call that like post or.
Okay. So as you're doing the topological sort, as you're doing the DepthFirst search, whenever you post-visit a vertex, you're giving it a post time, have a list that you're creating of all the vertices in topological order. As soon as you post-visit a vertex, that means it has a small post time. Stick it at the beginning of that list and build the list backwards. So the first vertex to go into the list would be C. So as you're doing it, C was the first one we post-visited, so it's at the end of the list. And then F is the next, and then you build the list backwards, and A comes at the beginning. So you can build it as you're searching. In fact, you don't even need the numbers. Just in post-visit, you just throw that vertex onto the list and build the list backwards. So when the time it takes to search the graph, you've generated the topological sort. Now, where people go wrong on DAG algorithms is they realize they need a recursive algorithm to solve the problem, and so they try to design one. But for DAG algorithms, the only recursion you need is the DepthFirst search to do the sort. Once you've got it sorted, it becomes iterative. And if you find yourself trying to do any recursion other than the DepthFirst search on this caddis problem, you're going about the wrong way. do a depth-first search to sort, then use that sort to make the DAG algorithm fast. So again, I'm going to skip over the complexity. We'll come back to that. And another way to linearize, we'll come back to that. Let's talk about actually algorithms on DAGs. Like I said, the steps are to topologically sort the DAG, then do a non-recursive computation on each vertex in sorted order, or in each vertex in reverse order. Sometimes you have to reverse the DAG, depending on the algorithm. So if you got a directed graph, sometimes after you've done the topological sort, you're going to need to take the list and reverse it so the arrows point in the opposite direction so that it's fast to go from, in the initial configuration, it's fast to go from sources to sinks. Sometimes you need to be fast in the other direction. So it may be necessary to reverse. That can be done quickly in linear time. And like I say, for some reasons, students often ignore this advice. Rather than taking the time to understand how this works and doing it, they just try to invent their own way and end up with really inefficient algorithms, usually exponential. Okay, so let's take an example here. This is meant to represent a spreadsheet. So the circles, the vertices, are the cells in the spreadsheet. And so what you think of is this is a spreadsheet where we've got a cell that contains a 2 and a cell that contains a 5. And then this cell says add these 2 cells. So the black numbers are what's actually stored in the cell. The white number is what's calculated by the spreadsheet and displayed by the spreadsheet. So this cell contains a formula that says equals A plus E. But it displays a 7 because A plus E is 7. So we take these 2 cells and add them. We take the value of this cell and multiply, the value of these 2 cells and multiply, and then you add them at the end. Now what do the arrows represent? Yeah? Yeah, it's a dependency. So if B depends on A, there's an edge from A to B. So A points, every vertex has an arrow, has an edge to all the other the vertices that depend on it. So you're thinking about 3,500 right now. You did a spreadsheet, and one of the fundamental operations was to, when a cell changes, you want to efficiently update the cells that depend on it. And you may remember that to help you do that, the code that you were given in 3,500, there was a method in the spreadsheet class that you were supposed to use. What that method did was a topological sort. It determined for you the correct order in which to evaluate things. So that was doing a topological sort for you, and then you were leveraging that. So suppose vertex A changes from 2 to 7. What cells need to be updated? Let's see, this one, so A, D, B, F, C. All these are involved. This cell E doesn't matter. But in what order should it do it? So first it needs to update A, right? That's clear. We need to change that to a 7 and evaluate it so it gets a 7. Now, what should we do next? We better do D next. So we do that, so that becomes a 7, then we update this one, then we can update either of these in any order, and once those 2 are updated, we can do that. If you do the update in the opposite order, if you say, okay, let's update this cell, well, you go back, you say 14 plus 35 is 49, nothing will change. The idea is to update in the correct order. Well, the correct order is just consistent with the topological sort. So in this case, we just care about the vertices that are reachable from A. So we would do not a DepthFirst search, just a single explore starting at A and linearize in order of post time. And we would get something like A, D, F, B, C, or perhaps A, D, B, F, C. But we do the topological sort. And then you do a simple operation to each vertex in topological order. So you've got it sorted. Now you just go to vertex A and evaluate it. Okay, we've changed it to a 7. So we evaluate it, and that's a 7. Then we go to vertex D and reevaluate. Okay, that's 7 plus 5 is 12. So that becomes a 12. Then it says to go to vertex F. Okay, you look back at D and E. 12 times 5 is 60. Then you go to vertex B. You look back. What we're doing, multiply 7 times 12, that's 84. Finally, you update C, and you get 144. You did it in the correct order. You discovered the order by doing the topological sort. Then the actual updates themselves don't involve recursion. You don't have to, when you evaluate C, you don't have to recursively evaluate B and F first. You just assume they've already been updated. That's what DAG algorithms are supposed to be like. A simple, non-recursive operation applied to each vertex in this case, in topological order. Now, several times I use the word look back. You're evaluating D, you have to look back at A and look back at E. How do you do that? Arrows don't go in the right direction. How do you look back? Yeah? But in this graph itself, though, how do you efficiently find that A has an edge to D? Because adjacency matrix, adjacency list isn't set up for that. What operation you need to do the list before you start? I mentioned it earlier. No. Reverse. This is a case where, in addition to having the original graph, you need to have a reverse of the graph. A version of the graph where the arrowheads have been reversed. Just so that when you go to evaluate D, it's efficient to look back at A. And of course, in the spreadsheet example you did in 3500, your dependency graph class already was its own reverse. It had edges in both directions, essentially. Dependents, dependees, went both ways. So for this kind of update, it helps to also reverse the graph. Okay, here's another one I'm going to do. I want to label the graph with the number of distinct paths that lead from a source to a vertex. So why is A labeled as 1? I should go back. Okay, there's only one way to get from A to A. There's only one way to get from a source to A. There's only one source. What are the two ways to get to B? You can either go directly from A to B, or you can go A, D, B. There are two ways to do that. 3 ways to get to E, either A, B, E, A, D, E, or A, D, B, E, and so on. That's what I want to compute. That's my goal, and this is it in symbols. So what we're going to do is we're going to topologically sort it, which I did. And now what will we do with each vertex? What's the operation we want to apply? We're going to in topological order A, B, C, D, A, D, B, E, C, G, F. How do we decide what number to store with A? Right, so for a source, you see right there, we store 1. Okay, we did that. Now we look at D. How do you decide what number goes at D? Yeah?
So the sum of
the predecessors in the graph.
Yeah.
Right, you look back at all the things that have edges into D and add them up. In this case, there's only the A, so we add up the 1, and that's a 1. Then we go to the next one in topological order, B. We look back at all the things that have edges into B and add up their numbers. 1 plus 1 is 2. Now for E, we look back at B and D and add them up. How do we know that when we visit E or G or whatever, that its predecessors already have that number computed? What makes that happen? The topological sort. It's doing it in topological order. If you just pick some random order, say we want to try to do G right now. You go to add up, okay, we're going to add the number of ways to get to C and the number of ways to get to E, and they're not computed yet. This is where students are tempted to make a recursive call to compute them. And the problem is they got sort of the right idea, but they end up recomputing things over and over again, and you end up with exponential running time. Instead, topological sort, and then when you go to E, you're guaranteed that B and D have already been dealt with. So you add up the 2 and the 1, you get 3. Now you go to C. That's a 3. G, 3 plus 3 is 6. F is 6. Simple. Non-recursive, except for the sort. After the sort, the operation you apply at each vertex, non-recursive. Okay? Let me show you one more. Don't have much time. We'll revisit some of these next time. Okay, so each vertex has a price, labeled in white. Each vertex has a cost, labeled in yellow. That's the highest price you can reach from a vertex. So F's cost has to be its price, because you can't go anywhere from F. A's price is the highest cost you can reach, so it's basically the highest cost in the whole thing. So if you were computing the yellow from the white, in what order would you go? Basically, decide what goes in A, the yellow thing that goes with A, you've got to find the highest white in the entire graph. To decide what yellow goes with E, you've got to find the highest white one in the part of the graph you can reach from E. So if we're going to, say we topologically sorted, what operation do we need to apply to these vertices, and in what order? Yeah?
Oh, sorry.
Oh, no. Yeah?
You need to find like the highest price of its direct children, but you need to start at the back.
Right. We want to work backwards. And when you work backwards, you all you have to look at is the highest white of your children, not your grandchildren or anything like that. So let's back it off here. We will reverse sort it, F to A. We start at F. What's the highest white number you can reach from F? Well, it's just 2. Okay. G compares its 2 and the yellow 2 with F and gets a 2. We're just taking the max. C, it's going to take the max of the white 6 and the yellow 2 it can reach. That's a 6. What's E going to do? E is going to look at its 1 and these 2 yellow things that are guaranteed to have been computed. Takes the max and 6, and we just work backwards that way. So that's a case where you work backwards. In that case, we didn't have to reverse the graph either. We compute things for the sinks and work back to the sources. The other previous 2 examples, we started from the sources and worked toward the sinks. It just depends on how the problem's defined. It's generally easy to work backwards because you don't have to reverse the graph. All right, so that was a quick tour. We'll back up on Tuesday and go over what I skipped over.